We need to look at the equation solver for our finite element process. The equation solver is the engine that drives the whole finite element code. It's often a small part of the total number of lines of program, but usually occupies a large fraction of the actual execution time. We'll deal with the topics here. I like to set the background a bit by talking about different types of solvers and then showing that your physical problems fall into 4 categories in the linear problem case. We'll compare linear equation solvers and the way that the information is stored, which is often critical. We'll talk about the fundamental advantage of a triangular form of the coefficients of the equations. We'll look at the dominant solver, which is Gauss elimination, and this is what has dominated now in linear static problems worldwide. There was a thought that with vector processing computers that we might go to iteration methods more, even in linear problems, but that hasn't happened yet. It appears now we're headed more toward parallel processing, and I think that the Gauss elimination will still stay at the front. But I do discuss several of the iteration methods so that we have some general background on those, and then we'll have a problem session. We'll start out general and then gradually get more specific to our case. There are, in general, 3 kinds of equation solvers. There are the static stress type, using the equation that we'll use over and over. There are eigenvalue problems that have to do with vibration and buckling. And then there are transient equation solvers that involve dynamic motion, where you have damping, mass, and stiffness effects. From that standpoint, the static case looks like a special case where we are working on the stiffness and force terms and not as functions of time, and that is true. All of these problems can be either linear or nonlinear. The transient problems are solved by marching forward in time, actually by what are called finite difference methods in time. So a typical solver there will use finite differences in time, but will use finite elements in space. In our lecture series here, we're only considering static stress, so we're talking about the first type of equation up at the top. Many years ago, FREDHOLM decided that there were 4 alternatives in typical problem statements, mathematical problem statements. He was mostly interested in differential equations and integral equations, but the same ideas hold for matrix equations that we're interested in. Here's our general matrix law. For us, a linear static problem. And the 2 things that can take a branching behavior are the singularity of the stiffness matrix, and that is whether its determinant is 0 or not, and the presence of a force matrix, and whether that's 0 or not. I'll follow down the left branch first, where we're looking at conventional static stable structures that have a non-zero determinant. That means that the structure effectively can oppose loads and can carry loads in all directions. And if we furthermore take the branch where the load is non-zero, then we have a case where you have a stable static structure that has a non-zero load on it, and that would be stress analysis, where you get a unique answer. So it's a linear system that's an input-output system, and because of the linear nature, we're guaranteed that there's one answer. We're guaranteed that there's not 0 answers or 2 answers or n answers, which can happen in nonlinear systems and in more exotic systems. On the other hand, if you put a 0 load down this branch on a statically stable structure, then you get 0 here as an input driving the problem, and the answer is that the displacement result is 0. That's called a trivial problem or a trivial solution, and really isn't of much interest except that an unloaded body that's a nice strong body will stay where it is. Now, the other major branch is if the determinant of the stiffness coefficients is 0, shown here, and that means that the stiffness matrix has an inherent weakness in some direction. It's really a loss of stiffness in certain characteristic directions. I'm going to use a kind of a perforated K symbol there that's dashed lines so that it looks a little bit weak, and that's exactly what I mean to imply. Now you can furthermore either have the loading on the right hand side be 0 or not. The cleanest case is to the right, where you have a 0 load on a structure that has possibly some weaknesses in certain directions. And surprisingly, that does have displacement solutions. This comes up in buckling problems and in vibration problems, so-called normal modes. Those directions are certain characteristic directions of the problem, and this is called an eigenvalue problem. In German, that means characteristic value, and you do get more than one solution here. You may get as many as n such characteristic directions in a given problem, depending on how singular this matrix K is. We're not so interested in that problem in linear statics because we don't want a weak characteristic direction, which might correspond, for instance, to a rigid body mode in a static problem. And so we view that as not a good problem statement in linear statics. Lastly, a really pathological branch would be if you put a non-zero load, not 0, on a system that has these weaknesses. And in general, you will not get an answer here. Let's now concentrate on the problem of interest for us. That's the linear static solver, where the matrix of coefficients is not singular. In other words, the determinant of K is not 0. And we will also assume that we've put this problem in the standard form, where the unknowns are all clustered on the left side, and on the other hand, all the loads are known. If K is a particularly nice kind of matrix, namely real and symmetric and positive definite, then many good things happen. This is when you can get a unique solution. Now, positive definite by definition means that this triple product here is always greater than 0 if you calculate that for any non-zero displacement field. Physically, what that means is that strain energy is always positive, because we can associate that triple product exactly as strain energy if we put out front the factor 1/2. Now, the concept for solution will be that you would invert the matrix, multiply by the F vector, and that would give the solution. And sometimes we'll use this as a symbolic suggestion of the solution process, but in fact it's not done that way. It's done by triangular factorization, and we'll get into that in our next figures. Let's discuss some ways that you could solve the linear standard form. Back in high school, you often were given word problems that involved 3 equations and 3 unknowns. Usually the equations were not strongly coupled, as I noticed in my son's high school algebra book, but rather one of the equations was easy to figure out from the statement. For instance, the dog was always walking 10 feet behind the cat, and so you could immediately eliminate one variable in terms of one other variable. But more generally, you can solve such coupled equations by hand easily up to about a 3 by 3, and beyond that it starts getting difficult. So in college you were exposed to Cramer's rule, which is valid for tens of equations, it becomes really prohibitively expensive if you get over 60 equations. And at some point, less than 100 equations, you have to use the entire computer capacity of the world to do a problem. So Cramer's rule bombs out somewhere in the low tens, and wouldn't be advisable for essentially even anything but a trivial problem. So it's turned out not to be a modern useful method. Once in a while I'll use Cramer's method, though, for developing something within an element that has 3, 4, 5 equations. And so maybe that's the real use of Cramer's rule in the long run. But for any sizable problem, you start using Gauss elimination in its various forms. Now, it turns out that the high school elimination process that you did is really the same as Gauss elimination. But Gauss elimination has become rather formal in the application, in which you not only solve the equation simultaneously, but you do it with a certain data structure. For instance, you can break the stiffness matrix down into the product of two triangular matrices called L for lower triangular, and then the transpose of L. That would be the conventional Cholesky decomposition. It has one drawback in that the method will end up requiring a square rooting procedure on the main diagonal terms when you try to do this decomposition. In other words, this decomposition proceeds from left to right when you come to the numerics, and involves a lot of work. And those square root operations are usually prohibitive. So another method, sometimes called modified Cholesky or Gauss-Doolittle decomposition, proceeds from left to right, where you have a lower unit triangular matrix that has ones on the main diagonal, and then a separate diagonal matrix and the transpose of the lower unit matrix. Now that lower unit matrix I could sketch out in sort of a rough form here. Would have, for a 3 by 3 matrix, would have ones The triangular form is so advantageous that you need to just take a look at it and make sure this is imprinted in your memory. I'm going to propose that there exists a triangular matrix, a lower triangular matrix such as this, acting on an unknown vector and set equal to some known right-hand side. The reason this is so easy is it unravels from top down. And much like a cat that would pull a string from a ball of string, if you do it one piece at a time, one length of string at a time, ultimately you get the whole ball unraveled. So I'll claim that you could solve 10,000 equations and that the average viewer could program this in a matter of 20 minutes. And you'll see why here in a second. The first equation says 1x equals 7 because of the zeros. Well, even on a bad Monday, I can solve that one. That's that x equals 7. Then the second equation becomes 2 times that known number, 7, plus 3 times y equals 8. And I write that down here, and if we substitute 7 in that location, you get 3y equals 8 minus 14. And dividing out by the 3, you get y as 1/3 of that bracketed quantity. So you get y equals minus 2. Lastly, the bottom equation, like the others, involves known quantities at first. 4 times something that you know, which is 7. 5 times something that you know, which was minus 2. And then 6z equals 12. So in writing that below, you have known quantities here, and the only unknown is z this time. And you solve for it and directly have your answer. Now this generalizes, of course, and you can get a recursive form for this that we'll show you in a few minutes. But the key is that as it unravels, you only have one unknown in each equation. X in the first equation, y in the second, z in the third. And makes it a very straightforward solver process. Let's get into the details of the Gauss elimination that uses a modified Cholesky or Gauss-Doolittle decomposition of the stiffness. So we start out with the standard linear static stress problem where the unknowns are all on the left side and the knowns are on the right side. And then K is a nice matrix, real, symmetric, positive, definite. Then we know that we can do the decomposition implied here, which means that we need to find both a lower triangular matrix and a diagonal matrix. If I write those out in terms here of their components, then we do see the subscripting where you have the row column indexing that, for instance, in this first term L21, it's in the second row and the first column. Now the diagonal matrix is just what you'd expect also with terms down the diagonal. And these are the things that we need to determine. So obviously there's more than n quantities to be determined, and the reason is that you really have a matrix equation here and not a vector equation with which we're so accustomed. So beware that this is a lot of work to do what's called the decomposition here because of the n by n nature of the problem. After the decomposition phase, then we're ready to do the forward solution. This makes use of the decomposed stiffness matrix times the unknown vector equals the force. And what we do now is to create an artificial intermediate vector. And this was certainly a stroke of genius, where we take these terms and lump them together and call them a new vector x. When you've done that, you have the lower triangular matrix times x equals the force. And lo and behold, this is that nice triangular form that we love to get. So it's easy to solve then for this x vector. Once you have that, you use the definition for x itself, which is essentially an identity here, and you now solve for the unknown u displacements in terms of this now known x vector. And that's easy. It's easy because the multiplication of these two terms is itself an upper triangular matrix. And it will have a structure where there will be zeros all on the lower triangular part, but this time you're able to solve from bottom up. And again, that's easy. So that really completes the formal process of Gauss elimination, where you do decomposition, forward solution, and then back substitution. We now have the general idea of the Gauss elimination, but we need to be specific and actually find the formulas that deal with the terms in the matrices. On the left here is the stiffness matrix, which is now expanded out into the various terms. We have the lower triangular matrix, and then I'm taking the product of the diagonal matrix times the upper triangular matrix. And the result here, again, is an upper triangular matrix. The role of the diagonal terms is a multiplier which attacks the matrix behind it, row by row. And so the D11 term goes across this row, the D22 term goes across this row, and so on. But it doesn't destroy the upper triangular form. So now we have the product of two triangular matrices, and that actually does have some advantage. We're going to start the solution process for decomposition by looking at the upper left term K11, which is assumed known. And then the question is, can we find it by multiplying the row of this first matrix times the column of the second matrix? And when you do that, you get unity times D11, and then the remaining terms are 0. So you get literally K11 is D11. Now we want to think of it the other way around, that we're finding the D11 in terms of K11, which is known. So we have our first part of the solution. It works out that it's then best to move downward column-wise and find K211 by a similar multiplication, where we march across the second row in the first matrix and the first column of the second matrix. And again, there's only one term, and it only brings in one new quantity, which is L21, because we already know D11. And so you solve for L21 on the right, and now you have the second component of interest in the decomposed matrix. This follows on down that first column of the stiffness matrix, and you continue to get these single term equations here. There is a recursion relation then that helps organize the information on decomposing the first column of the stiffness matrix. And the first term was a special case, but beyond that we get this formula, and I'd like you to consider it for this region. And we knew there was a single law for the first term in the decomposition of that K. Then we have remaining the diagonal terms, for which there's another recursion formula that I'll show in a minute, and then the lower triangular area, number 4. Now this fourth region is really by far the most dominant region, because the other regions are only one component wide, whereas this one is actually an area of terms, which is of the order of n squared, where n is a number of equations. Now, it's possible, and I'll show you a computer code to do this later, to write this decomposed matrix as we decompose these regions and get the the L and the D matrix over here. It's possible to write them right back on top of the previously used terms in the stiffness matrix. And so as this problem unravels, you really only need to create one matrix in storage. Sometimes that's important because the storage of the stiffness terms is often the dominant storage use in the problem. And here are the recursion formulas that were promised. This one in the region 3 down the main diagonal, and this one for the region 4, which involves most of the terms really in the decomposition. And this is the expensive part. The reason being that there are in the interior here on the order of n multiplications. And you have to do this for that solid area which involves as many as n squared terms in a full matrix. And so it's conceivable that this could require as many as n cubed floating point operations. There is a way to beat that later on. We'll find that you can exploit something called bandwidth, where there are a lot of zeros and you don't get caught in quite as bad a shape as the full number n cubed. But nevertheless, the number of calculations here will often dwarf all the other calculations in a linear static problem. It might cost 95% of the total cost of your finite element run. And isn't that interesting? We can write it out, at least for a full matrix, in rather simple form here. And so here's where the brunt of calculation falls. I used to use a lot of programming in my finite element training and expose the attendees to writing their own finite element program. I've backed off from that in recent years because I think more and more the engineer should understand the modeling aspects, the theoretical aspects, and I think much of the battle is over on the programming front. For instance, the equation solvers are available commercially, the graphics commercially, and so on. But nevertheless, the Fortran program for the equation solver here, the Gauss elimination solver, is still of some interest, and I do show it. And it's about the only thing that I would encourage an attendee to do on their own away from the training session. It would probably take about 4 hours to do the Gauss elimination solver, and it would be of some value. Now the version we're going to show here is for the unbanded version where the matrix might be full. And to start with, we put down the decomposition program, which involves an n by n matrix K. You can come into this program then with a square, real, symmetric, positive, definite matrix K, and then when the program is done, it will have written the diagonal decomposed matrix on the diagonal of the old K matrix, and it will write the lower triangular form on the lower triangular part of the K matrix. The interesting thing about this program is that it only really involves 21 executable Fortran statements, and yet this is the most expensive part of linear static solving. If you convert this into a banded form that would exploit zeros in the matrix, then it would take some more lines of logic, but would be somewhat similar. It's a much more difficult problem, and I don't try to teach that though. Now let's look at the logic in the forward solution. Here we have the decomposed lower triangular stiffness terms. We have the intermediate vector that's been artificially introduced, and then the known forces. So when we expand that equation into its components, we can see that this is the one that is easily solved from top down. For instance, the first equation is merely x1 equals f1 and is a direct solution. Then the second equation involves the known force on the right-hand side and then some previously uncovered terms. So this progresses from top to bottom. We can identify a recursion formula shown here. There are as many as n squared floating point operations involved here, because this summation can involve as many as n products, and you have to do it n times for these different components of x. Back substitution is our remaining task. Here we show the equation that really was an identity. It was the definition of the intermediate vector x, but we treat x now as a right-hand side that is known, and now we want to recover the physical displacements in the problem. When we write out the diagonal times the upper triangular collection of decomposed terms, we get this triangular form, which uncouples from the bottom up. And so we therefore can solve sequentially again. The bottom equation is just dnn times un equals xn, which is known. Then, knowing that first term, we go into the second equation, which involves other previously determined terms, and we can solve for the un minus 1 in that case. You continue on up the ladder to un minus 2, n minus 3, and so on until you're finished. We again get a recursion formula. And this one, like the forward solution, requires up to n squared floating point operations, because there can be as many as n terms in this sum, and this process has to be repeated for as many as n physical displacement components. This again is a cheaper task than the decomposition was. I'll show the Fortran program for the forward solution and the back substitution here. Again, this is simpler than one might think, considering the importance to the whole process. 20 executable lines, only a few comment lines added here. They're really the two loops this time that have to do with the forward solution here, and then the back substitution here. The code might even have been slightly simpler if the conventional Fortran loop would have checked for the index before it executes the first calculations and proceeds to the end of the first loop, because that's what makes the first cycle through exceptional and requires a little extra logic. So in some other languages, you might be able to make this programming even more compact. I'd like to give an example now where we will take a simple 3x3 matrix and find the solution. I've made this come out in round numbers so that it doesn't get too complicated algebraically. But our job will be to factorize the stiffness matrix first, then do the forward and the back solutions. So we use the standard form that we've gotten used to here, and again we will group together the latter two terms in the product to give an upper triangular matrix. I'll write this matrix law out term by term here. And what we would like to do now is solve first for the decomposition terms corresponding to the upper left part of the stiffness. Now that amounts to following this row times this column. And in that case, you only have one term on the left and one term on the right. 1 equals D11. Next, we try to decompose this term. We find that it, on the right side, has to equal this row times this column, and again, yielding only this simple equation. Now, we already know D11, so now we solve for L21, and we get the value 2. The third term is equally easy, this row times this column, and gives us L31, which is unity. The remaining 3 decomposition terms are a little more complicated, and I'll basically write the answers down. Here we have the expression for the second diagonal term occurring as an unknown here in terms of known things. Then we want to go for the term in the lower triangular portion, region number 4, involved here, and everything else is known. Finally, we get the last diagonal term. And those have all come out nicely in round numbers. I've collected those here and show it as a lower unit triangle as well as the upper unit triangular form here. And then the diagonal terms occurring in between. Remember now, this is the most difficult part of the whole process and the most expensive. Once you have that, now we can go into the forward solution shown here and finally the back substitution. So we'll use the L1 matrix to look at our forward solution. We use that matrix there, introducing this intermediate vector, and with our original physical loads. That's the one that solves from top to bottom with x1 equals 8 as the trivial first equation. Second equation